Chlorine was first prepared by Scheele in 1774 by the action of hydrochloric acid on manganese dioxide. In 1810, Davy established its elementary nature and suggested the name chlorine on account of its color. The name chlorine is derived from the Greek word chloris, which means greenish-yellow. Chlorine is a greenish-yellow gas. In the laboratory, chlorine is prepared by one of several methods. The first method is to heat manganese dioxide with concentrated hydrochloric acid. However, a mixture of concentrated sulfuric acid and common salt is used in place of concentrated hydrochloric acid. Another method is by the action of hydrochloric acid on bleaching powder. Chlorine can also be prepared by the action of excess hydrochloric acid on potassium permanganate. And by the action of hydrochloric acid on lead dioxide. Commercially, chlorine is manufactured by two processes. One process is the electrolytic process, in which chlorine is obtained by the electrolysis of brine in a Nelson cell. This is the cheapest method and gives the purest chlorine. Another method is Deacon's process. In this process, chlorine is obtained by the oxidation of hydrochloric acid in the presence of cuprous chloride at 723 Kelvin and 1 atmospheric pressure. Let us now look at the physical properties of chlorine. It is a greenish-yellow gas with a pungent smell. It is poisonous in nature. It has a melting point of 171.6 Kelvin and a boiling point of 239.11 Kelvin. It can be easily liquefied. It is about 2 to 5 times as heavy as air. It is fairly soluble in water. Now let us look at the chemical properties of chlorine. Chlorine dissolves in water to give a strongly smelling yellow solution called chlorine water. Chlorine water loses its yellow color on standing in sunlight due to the formation of a mixture of hydrochloric acid and hypochlorous acid. Hypochlorous acid, being unstable, decomposes and gives nascent oxygen. The nascent oxygen so formed is responsible for the oxidizing and bleaching properties of chlorine. It combines directly with all non-metals except nitrogen, oxygen and carbon. The equations for the reaction of chlorine with some non-metals like phosphorus and sulfur are shown here. Chlorine reacts readily with most metals to form their corresponding chlorides. the equations for the reaction of chlorine with some metals like sodium, iron, aluminium and zinc are shown here. It has great affinity for hydrogen. It combines with hydrogen in the presence of light with an explosion to form hydrochloric acid. It decomposes several hydrogen compounds to form hydrochloric acid. For example, it decomposes hydrogen sulfide to hydrochloric acid and sulfur. It is a good oxidizing agent. It oxidizes ferrous to ferric, sulfides to sulfates, sulfur dioxide to sulfuric acid, and iodine to iodic acid. As mentioned earlier, moist chlorine, due to the liberation of nascent oxygen, acts as a powerful bleaching agent. Its bleaching action is said to be permanent and oxidizing in character. Moist chlorine bleaches vegetable or organic matter. It forms addition compounds like sulfuryl chloride with sulfur dioxide and carbonyl chloride with carbon monoxide. It forms ammonium chloride with an excess of ammonia and the explosive nitrogen trichloride with an excess of chlorine. It forms bleaching powder with slaked lime. It forms sodium hypochlorite with cold and dilute sodium hydroxide and sodium chlorate with hot and concentrated sodium hydroxide. It reacts with saturated hydrocarbons to give substitution products and addition products with unsaturated hydrocarbons. For example, it reacts with methane in the presence of sunlight or ultraviolet light to produce chloromethane and ethene to 1,2-dichloroethane. Now let us look at the uses of chlorine. Chlorine is used as a bleaching agent in the wood pulp, cotton, and textile industries. To sterilize drinking water. As a germicide and disinfectant in swimming pools. In the extraction of gold and platinum. In the manufacture of bleaching powder, chloroform, carbon tetrachloride, dyes, drugs, rubber, etc. In the preparation of poisonous gases such as phosgene, tear gas, and mustard gas. In 1648, Glauber became the first to prepare hydrogen chloride by heating a mixture of common salt and concentrated sulfuric acid. In 1810, Davy showed that it is a compound of hydrogen and chlorine. Hydrogen chloride is prepared in the laboratory by treating sodium chloride with concentrated sulfuric acid. The reaction mixture, consisting of concentrated sulfuric acid and sodium chloride, is first heated to 420 Kelvin. Sodium bisulfate is obtained, which is insoluble and thus prevents further reaction. Hence, sodium bisulfate is mixed with more sodium chloride and further heated to a high temperature of about 823 Kelvin to give HCl gas and soluble sodium sulfate. The HCl gas is dried by passing it through concentrated sulfuric acid. Note that HCl is not dried either over phosphorus pentoxide or quicklime because it reacts with them both, as shown here. Let us now study the properties of hydrogen chloride. Hydrogen chloride is a colorless gas with a pungent odor. It liquefies to a colorless liquid at 189 Kelvin and freezes to a white solid at 159 Kelvin. It is highly soluble in water. At room temperature, 1 volume of water dissolves 452 volumes of hydrogen chloride. An aqueous solution of hydrogen chloride is called hydrochloric acid. An aqueous solution of hydrogen chloride undergoes ionization to produce hydronium ions and chloride ions. The ionization of hydrochloric acid, along with the Ka value, is shown here. The larger value of the dissociation constant indicates that hydrochloric acid is a strong acid. In other words, on account of its ability to dissociate almost 100% to produce hydronium ions, it is considered a strong acid. Hydrochloric acid reacts with metals and alkalis to form chlorides. For example, it reacts with zinc to form zinc chloride and with sodium hydroxide to form sodium chloride. Note that hydrochloric acid reacts with iron to form ferrous chloride and not ferric chloride. This is because the hydrogen liberated prevents the formation of ferric chloride. Hydrochloric acid reacts with ammonia to form dense white fumes of ammonium chloride. You know that noble metals such as gold and platinum are insoluble even in hot and concentrated nitric acid. However, noble metals dissolve in a concentrated solution of nitric acid and hydrochloric acid taken in the ratio of 1:3. This solution is called aqua regia. Aqua regia produces nascent chlorine, due to which noble metals dissolve in it. The nascent chlorine attacks these noble metals to form chlorides, which eventually form soluble complexes on reacting with hydrochloric acid, as shown in these equations. Hydrochloric acid decomposes salts of weaker acids, such as sodium carbonate, sodium bicarbonate, and sodium sulfite. You can see from the balanced chemical equations that hydrochloric acid decomposes sodium carbonate and sodium bicarbonate to sodium chloride, carbon dioxide, and water, while it decomposes sodium sulfite to sodium chloride, sulfur dioxide, and water. Let us now look at the uses of the aqueous solution of hydrogen chloride or hydrochloric acid. It is used in the manufacture of chlorine and chlorides like ammonium chloride. It is also used in the manufacture of glucose from cornstarch. It is used for extracting glue from bones and purifying bone black. It is used as a laboratory reagent and in medicines. A saturated solution of zinc chloride in dilute hydrochloric acid is used to remove the impurities on a metal surface before soldering or electroplating. Halogens usually form 4 series of oxo acids, namely hypohalous acids, halous acids, halic acids, and perhalic acids, which are represented by the general formulae HOX, HOXO, HOXO2, and HOXO3, as shown here. X represents the halogen, which may be fluorine, chlorine, bromine, or iodine. Most oxo acids of halogens cannot be isolated in pure state. They are stable in their aqueous solutions or in the form of their salts. The table here lists the formulae and oxidation states of the 4 series of oxo acids of each halogen. Note the oxidation state of the central atom, fluorine, chlorine, bromine, and iodine in each oxo acid. Examine the structures of the oxo acids given here. Let us now discuss some important features of the structures of the oxo acids of halogens. In all of these oxo acids, the central halogen atom is sp3 hybridized. One XOH bond is essentially present in every oxo acid. In most of these oxo acids, X double bond O bonds are present. The double bond present in an oxo acid between the central halogen atom and oxygen is d-pi, p-pi in nature. The first series, that is, hypohalous acids, include hypofluorous acid, hypochlorous acid, hypobromous acid, and hypoiodous acid. The halogen has the oxidation state of +1 in hypohalous acids. The respective hypohalite ions have a linear shape owing to the presence of 3 lone pairs of electrons on the central halogen atom, as shown here. Note that the hypohalous acids, being less stable, tend to form halic acids. Note that the only oxo acid of fluorine is hypofluorous acid. No higher oxo acid of fluorine is known due to the absence of d orbitals in the fluorine atom. The second series, that is, halous acids, includes only chlorous acid. The chlorine in chlorous acid has the oxidation state of +3. The chlorite ion has a V shape owing to the presence of 2 lone pairs on the central chlorine atom. The third series, that is, halic acids, includes chloric acid, bromic acid, and iodic acid. The halogen has the oxidation state of +5 in these oxo acids. The respective halate ions are pyramidal in shape owing to the presence of a lone pair of electrons on the central halogen atom, as shown here. The fourth series, that is, perhalic acids, includes perchloric acid, perbromic acid, and periodic acid. The oxidation state of the halogen in these oxoacids is +7. The shape of the perhalate ion is tetrahedral. In any series of oxoacids of halogens, the first member possesses high acidic strength. This is due to the high electronegativity and small size of the respective halogens, fluorine in the hypohalous acid series and chlorine in the other series of oxoacids. For example, among perhalic acids, perchloric acid has high acidic strength. As chlorine is more electronegative than bromine or iodine, the shared electron pair lies relatively nearer to chlorine in a ClO bond than bromine in a BrO bond or iodine in an IO bond. As a consequence, the OH bond becomes much weaker in case of perchloric acid, thereby facilitating the release of a proton readily. Let us now see how the acidic strength varies for the oxoacids having the same central halogen atom. The acidic strength of an oxoacid increases with an increase in the oxidation number of the halogen. For example, among the 4 oxoacids of chlorine, the acidic strength increases markedly from hypochlorous acid to perchloric acid. Hence, we can conclude that perchloric acid is the strongest acid among all the oxoacids of halogens.